Close your eyes for a moment and picture Earth. Blue oceans stretching across 70% of the surface. Green and brown continents dotted with forests, deserts, mountains. White clouds swirling in predictable patterns. A single yellow sun rising each morning, setting each evening. Temperatures that hover in a range where water remains liquid on the surface. An atmosphere you can breathe without a second thought. Seasons that follow a rhythm you can set your calendar to. Now open your eyes and try to imagine something completely different. A world where molten iron rains from the sky in sideways torrents, driven by winds faster than the speed of sound. A planet so utterly black, it absorbs 99% of all light that touches its surface. Darker than coal, darker than the most advanced light-absorbing materials ever created in laboratories. A world with rings so massive they stretch 200 times wider than Saturn's iconic bands, spanning a distance greater than the orbit of Earth around the Sun. A planet orbiting not one sun but two, rising and setting in an alien dance that would mesmerize any observer standing on its surface. These are not fantasies from science fiction novels. They are not the imaginings of visionary filmmakers or the speculations of creative writers. They are real places, confirmed worlds, objects that exist in our universe right now, orbiting distant stars, following the same laws of physics that govern our own planet, yet producing outcomes so extreme and unexpected that they challenge everything astronomers thought they understood about how planets form, how they evolve, and what conditions are actually possible in the cosmic environment. And while the internet debates missions to Mars or speculates about life on the moons of Jupiter, something far more profound has been unfolding quietly in the astronomical community over the past 3 decades. A revolution in planetary science. The discovery of thousands upon thousands of alien worlds, each one adding a new data point to our understanding of what planets can be, how diverse planetary systems truly are, and just how strange the universe becomes when you look beyond the familiar confines of our own solar neighborhood. Welcome to the world of exoplanets, worlds beyond our solar system, places that defy imagination, rewrite textbooks, and force scientists to continuously expand their understanding of what is possible when gravity, chemistry, and time come together under conditions radically different from those that shaped Earth. Before we begin this journey through the most bizarre alien worlds ever discovered, I need you to do something. Pause for a moment and leave a comment below. Tell me where you're watching from. What time is it for you right now? And here's the important question. Which type of exoplanet do you find most fascinating? Are you drawn to the hellish hot Jupiters that orbit so close to their stars they're being slowly vaporized? The rogue planets wandering through empty interstellar space with no sun to call home? The ocean worlds that might hide life beneath global seas? Or perhaps the zombie planets circling dead stars, the last remnants of solar systems that died billions of years ago? Drop your answer in the comments. I read every single one, and your engagement genuinely helps YouTube's algorithm show this video to more people who share your curiosity about the universe. And if you haven't subscribed yet, now would be the perfect time. Because over the next 18,000 words, we're going to explore places that will change how you think about planets, about the potential for life beyond Earth, and about our own planet's place in a cosmos far stranger than anyone imagined just a generation ago. 30 years ago, humanity's knowledge of planets was limited to exactly 9 worlds. The familiar lineup orbiting our Sun: Mercury, baking in solar radiation; Venus, shrouded in crushing carbon dioxide; Earth, our blue marble; Mars, the rusty red neighbour; the gas giants Jupiter and Saturn; the ice giants Uranus and Neptune; and Pluto, still considered a planet at the time, frozen at the edge of the known solar system. That was it, 9 worlds. That was the entire planetary census for all of human history. Every civilization that had ever looked up at the night sky, every astronomer who had ever pointed a telescope toward the stars, every scientist who had theorized about the nature of the cosmos, they all knew of exactly the same 9 planets. no more, no less. The idea that other stars might host planets of their own was not new. Philosophers had speculated about it for centuries. Giordano Bruno, the Italian monk and philosopher, was burned at the stake in 1600 partly for suggesting that stars were distant suns surrounded by their own worlds. Isaac Newton's laws of gravity implied that planetary systems should be common. By the 20th century, most astronomers assumed exoplanets must exist, but assumption is not the same as detection. And despite decades of searching, despite increasingly sophisticated telescopes and detection methods, no one had managed to confirm a single planet beyond our solar system. Until 1995. On October 6th of that year, astronomers Michel Mayor and Didier Queloz stood before the scientific community and announced something that should have been impossible according to conventional planetary formation models. They had discovered a planet orbiting the star 51 Pegasi, located about 50 light-years from Earth in the constellation Pegasus. They named it 51 Pegasi b, and it was absolutely nothing like anything in our solar system. The planet was massive, roughly half the mass of Jupiter, the largest planet in our solar system. But unlike Jupiter, which orbits the Sun at a comfortable distance of 483 million miles and takes nearly 12 years to complete one orbit, this new world hugged its parent star at a distance of just 4.8 million miles, and it completed its entire orbit in just 4.2 Earth days. Think about that for a moment. 4 days. That's how long it takes this massive gas giant to race around its star. By comparison, Mercury, the closest planet to our Sun, takes 88 days to orbit. This newly discovered world was moving at velocities that seemed absurd, experiencing temperatures that would vaporize most known materials, existing in a region where planetary formation theory said large planets should not and could not form. The astronomical community was stunned. Some were skeptical. The detection method used by Mayor and Queloz relied on something called the radial velocity technique, also known as the Doppler method. The basic principle is elegant. As a planet orbits its star, it doesn't actually orbit in a perfect circle while the star remains stationary. Instead, both the star and the planet orbit their common center of mass. For a massive planet, this causes the star to wobble ever so slightly, moving toward us and away from us as the planet tugs it around. This wobble affects the light we receive from the star. When the star moves toward us, its light gets compressed, shifting toward the blue end of the spectrum. When it moves away, the light stretches, shifting toward the red. By measuring these tiny shifts in the star's spectral lines, astronomers can detect the presence of an unseen planet and calculate its mass and orbital period. The precision required for this technique is extraordinary. We're talking about detecting velocity changes of just meters per second in objects that are tens or hundreds of light years away. It's like standing in New York and measuring the speed of a car in Los Angeles by analyzing the pitch of its engine sound. The technical achievement alone was remarkable, but the implications were staggering. If a hot Jupiter could exist orbiting 51 Pegasi, then planetary systems were far more diverse than our single example suggested. The rules of planet formation needed to be rewritten. The assumptions that had guided decades of theoretical work needed to be reconsidered. And most importantly, if planets could form in configurations we never predicted, then the universe might be full of worlds stranger than we had ever imagined. The discovery of 51 Pegasi b was like finding the first crack in a dam. Within months, the flood began. Astronomers around the world turned their telescopes towards sun-like stars and started finding planets everywhere. Not just one or two, dozens, then hundreds, then thousands. By 1996, less than a year after the first confirmed hot Jupiter, several more had been discovered. These weren't flukes or observational errors. They were real objects, confirmed by multiple independent observations using multiple techniques. Hot Jupiters were not only possible, they appeared to be relatively common in the galaxy. In 2009, NASA launched the Kepler Space Telescope with a single focused mission: stare at a patch of sky containing about 150,000 stars and watch for planets. The technique Kepler used was different from radial velocity. It employed transit photometry, watching for the tiny dip in a star's brightness that occurs when a planet passes in front of it from our perspective. The transit method is beautifully simple in concept, but brutally demanding in execution. When a planet transits its star, it blocks a tiny fraction of the star's light. For an Earth-sized planet passing in front of a Sun-sized star, the brightness dips by about 0.01%. That's 1 part in 10,000. Detecting that requires measuring stellar brightness with incredible precision, filtering out all sources of noise, and doing it continuously over long periods to catch multiple transits and confirm the planet's orbital period. Kepler revolutionized exoplanet science. Over its operational lifetime, from 2009 to 2018, it discovered more than 2,600 confirmed planets and identified thousands more candidates still awaiting confirmation. The sheer volume of data transformed exoplanet research from the study of individual oddities to statistical analysis of planetary populations. Astronomers could finally ask questions like, what percentage of stars have planets? How common are Earth-sized worlds? What is the typical architecture of a planetary system? The answers emerging from Kepler's data were surprising. Planets appear to be the rule, not the exception. Nearly every star in our galaxy likely hosts at least one planet. The Milky Way, containing between 100 and 400 billion stars, probably harbors hundreds of billions of planets. Some estimates push that number into the trillions when you account for rogue planets that don't orbit any star at all. But quantity was only part of the story. Diversity was the real revelation. Kepler found planets of every conceivable size and orbital configuration. Super-Earths, rocky worlds larger than Earth but smaller than Neptune, which don't exist in our solar system at all. Mini-Neptunes, gas-enveloped worlds intermediate between Earth and the ice giants. Planets orbiting so close to their stars they complete an orbit in less than a day. Planets in the habitable zone, where liquid water could exist on the surface. Circumbinary planets orbiting 2 stars at once, like Tatooine from Star Wars. Other detection methods added to the growing catalogue. Direct imaging, though technically challenging because stars outshine planets by factors of billions, began confirming large young planets that still glow with heat from their formation. By using adaptive optics to correct for atmospheric distortion and coronagraphs to block the star's overwhelming light, astronomers captured actual photographs of exoplanets. These images showed worlds in wide orbits around young stars, giant planets 5 or 10 times Jupiter's mass glowing in infrared light, slowly cooling over millions of years. Gravitational microlensing offered yet another window. This technique exploits Einstein's general relativity, specifically the prediction that mass bends space-time and can act as a lens. When a star passes in front of a more distant background star, from our perspective, the foreground star's gravity can magnify and distort the background star's light. If the foreground star has planets, they create additional brief spikes in the magnification signal. Microlensing can detect planets at vast distances across the galaxy, including free-floating rogue planets with no host star at all. By late 2025, the confirmed exoplanet count exceeded 6,000 worlds. The NASA Exoplanet Archive, the official repository for confirmed discoveries, continues adding new entries weekly. But these numbers, impressive as they are, barely scratch the surface. Current detection methods are biased toward finding certain types of planets, large ones in close orbits that produce strong signals. The true population of planets in our galaxy, including small rocky worlds in distant orbits that current technology struggles to detect, is almost certainly orders of magnitude larger. Now that we understand how we find these alien worlds, let's talk about what we've actually found. And we're going to start with one of the most visually spectacular and physically extreme planets ever discovered, WASP 76b. Imagine standing on the surface of this world. If it had a surface you could stand on, which it doesn't. You're on the day side, facing the star. The temperature here exceeds 2400 degrees Celsius. That's hot enough to vaporize iron. Hot enough to melt rock. Hot enough that if you somehow existed in this environment, your body would be instantly incinerated, and your atoms would join the roiling atmospheric chaos surrounding you. But you can't look around because there is no you, there is no solid surface. There is only an ever-deepening atmosphere of hydrogen and helium mixed with vaporized metals, all compressed under enormous pressure, all moving in ways that create weather patterns unlike anything on Earth. WASP 76b is what astronomers call an ultra-hot Jupiter. It's slightly less massive than Jupiter, but significantly larger in radius because the intense heat from its nearby star has puffed up its atmosphere. The planet orbits its star, WASP 76, at a distance of just 0.033 astronomical units. For comparison, Earth orbits the Sun at 1 astronomical unit. Mercury, the closest planet to our Sun, orbits at 0.39 astronomical units. WASP 76b is more than 10 times closer to its star than Mercury is to the Sun. At that distance, the planet is tidally locked, just like the Moon is to Earth. One side of WASP 76b permanently faces its star, experiencing eternal day. The other side faces away, experiencing eternal night. There is no sunrise or sunset, no rotation that brings relief from the heat or respite from the cold. The day side bakes under constant stellar radiation. The night side, deprived of direct heat, cools to temperatures hundreds of degrees lower. This temperature difference creates winds, not gentle breezes, not even hurricane-force winds. We're talking about atmospheric currents moving at speeds exceeding 18,000 kilometers per hour. That's about 5 kilometers per second, faster than the speed of sound on Earth by a factor of 15. These winds race from the day side to the night side, transporting heat, carrying vaporized metals, redistributing atmospheric material across the planet in a continuous violent circulation. And here's where it gets truly alien. On the day side, iron exists as vapor mixed into the atmosphere, but as this metal-laden air is swept around to the night side by those supersonic winds, it cools. When it cools, the iron vapor condenses. It transitions from gas to liquid droplets. And those droplets fall. It rains iron on the night side of WASP 76b. Not water, not any substance we would recognize as precipitation on Earth. Molten iron droplets, glowing red hot even as they condense, falling sideways through the howling wind, possibly evaporating again before they descend too deep into the hotter lower atmosphere, only to be carried back toward the day side where the cycle repeats. The discovery of this iron rain was made through high-resolution spectroscopy using the espresso instrument on the European Southern Observatory's Very Large Telescope in Chile. Astronomers observed WASP 76b as it transited its star, passing between us and the star, so that starlight filtered through the planet's atmosphere before reaching our telescopes. By analysing that light with extraordinary precision, they detected the signatures of iron vapor in the atmosphere. But here's what made it remarkable. They found iron signatures on the day side, but not on the night side. The iron wasn't gone. It had changed state. The day side showed gaseous iron absorption lines in the spectrum. The night side showed no such lines because the iron had condensed into droplets that don't produce the same spectroscopic signature. The only explanation that fit the data was precipitation. The iron was literally raining out of the atmosphere on the night side, only to be replenished continuously by the circulation from the day side. This is planetary science at its most mind-bending. We're not just detecting planets anymore, We're measuring their atmospheric composition, tracking their weather patterns, identifying precipitation cycles of substances that, on Earth, exist only in molten form in volcanic systems or industrial furnaces. We're studying alien meteorology on worlds hundreds of light years away. If WASP-76b is the planet of fire and iron storms, then TRES-2b is the planet of absolute darkness. This world holds a distinction that sounds like it came from a gothic horror novel. It is the darkest exoplanet ever discovered. Darker than coal, darker than the blackest acrylic paint, darker than any naturally occurring substance on Earth. TRES-2b reflects less than 1% of the light that strikes it. To understand how extraordinary that is, consider Earth. Our planet has an albedo, a measure of reflectivity, of about 30%. 30% of the sunlight that hits Earth bounces back into space, reflected by clouds, ice oceans, and land surfaces. The Moon, which appears dull grey to our eyes, reflects about 12% of the light hitting it. Even the darkest known object in our solar system, one of Saturn's moons, named Iapetus, which has a bizarrely dark hemisphere, reflects about 4% of incident light on its darkest regions. TRES-2b reflects less than 1%, possibly as little as 0.1% according to some measurements. This planet absorbs almost everything that touches it. Photons from its star impact the upper atmosphere and simply vanish, their energy converted to heat rather than bouncing back toward any observer. What could cause such extreme darkness? TRES-2b is another hot Jupiter, orbiting very close to its parent star, about 3 million miles, close enough that its atmospheric temperature exceeds 1,800 degrees Celsius. At these temperatures, most clouds that might reflect light, such as reflective silicate or water vapor clouds, cannot form. They're too hot. The molecules break apart. What remains is a hazy atmosphere, rich in light-absorbing chemicals. The leading hypothesis involves something called vaporized sodium and potassium, along with gaseous titanium oxide. On Earth, titanium oxide is used as a pigment in white paint because of its highly reflective properties. But that's solid titanium oxide. In gaseous form, at extreme temperatures, in the unique chemical environment of an ultra-hot Jupiter's atmosphere, titanium oxide may actually become an incredibly effective light absorber. Add to that the possibility of exotic carbon-based hazes, molecules like soot particles, or complex organic compounds that form under intense UV radiation, and you get an atmosphere that functions almost like a light trap. Photons enter the atmosphere, get scattered by molecules, encounter absorbing compounds at every interaction, and ultimately transfer their energy as heat rather than escaping back into space. Despite absorbing so much light, TRES-2b doesn't become an efficient radiator. This is another oddity. Normally, a planet that absorbs a lot of energy should heat up and then radiate that heat away as infrared light, reaching an equilibrium temperature. TRES-2b does radiate infrared, enough that astronomers have actually measured its thermal emission, but it retains more heat than models predict. Some energy budget that doesn't quite balance, as if the planet is somehow bottling up radiation more effectively than it should. The visual appearance of TRES-2b, if you could somehow hover nearby and observe it with human eyes, would be profoundly unsettling. The planet would appear as an almost perfect black sphere, silhouetted against the brilliant star behind it. You might detect a faint dull red glow from the heat, especially on the day side, giving it an ember-like quality, but there would be no blue, no white clouds, no reflective sheen, just blackness, an absence of light, a hole in space where a planet happens to exist. This raises an interesting question that goes beyond just the science of atmospheric chemistry. How many other dark planets exist out there that we haven't detected yet? Current exoplanet detection methods rely heavily on either transits or reflected light. A planet that doesn't reflect light is harder to find through direct imaging. If Trieste 2b had been slightly farther from its star, making transits less likely to occur from our viewing angle, we might never have discovered it. And if extremely dark planets are common, then our census of exoplanets could be systematically biased against finding them. There's something almost philosophical about a world that swallows light. It exists, it has mass, it orbits a star, it follows the laws of gravity and thermodynamics, but it refuses to participate in the most fundamental exchange of the visible universe, the reflection and scattering of photons that allows us to see. It is there, but hidden, detectable only through indirect effects. Now let's travel from darkness to one of the most visually iconic discoveries in exoplanet science, Kepler 16b, the real-world Tatooine. Anyone who grew up watching Star Wars remembers that scene. Young Luke Skywalker standing on a desert ridge, watching twin suns set over the horizon of his home planet Tatooine. It was pure science fiction, a visual flourish meant to emphasize the alien nature of the setting. But it turns out that George Lucas, intentionally or not, depicted something that actually exists in the universe. Kepler 16b is a circumbinary planet. That term breaks down into its Latin roots, circum meaning around and binary meaning two. This planet orbits not one star but two stars that themselves orbit each other. It's a planetary system within a binary star system, a configuration that sounds unstable and chaotic but turns out to be surprisingly common in the galaxy. The two stars of the Kepler 16 system are located about 200 light-years from Earth in the constellation Cygnus. They're both smaller and cooler than our Sun. The primary star has about 69% of the Sun's mass and is classified as a K-type orange dwarf. The secondary star is even smaller, just 20% of the Sun's mass, making it an M-type red dwarf. These two stars orbit each other every 41 days at a distance of about 0.22 astronomical units, roughly half the distance between Mercury and our Sun. Kepler 16b orbits both of these stars at a distance of 0.7 astronomical units, taking 229 days to complete one orbit. The planet itself is roughly Saturn's size and mass, a gas giant with no solid surface, far too cold to support life as we know it. But that's not what makes it fascinating. What captures the imagination is the sky. If you could somehow float in the upper atmosphere of Kepler 16b, you would see two suns moving across the sky. They wouldn't be identical. The primary star would appear orange and significantly brighter than the secondary, which would glow with a dull red hue. Depending on where the planet was in its orbit and where the two stars were in their mutual orbit, you might see them close together, moving almost as one. Or you might see them separated, rising and setting at different times, casting double shadows from any object between them and the cloud tops. The mechanics of this system are elegant once you understand them, but they initially seemed almost impossible. When astronomers first started thinking seriously about planet formation in binary star systems, the consensus was that it probably couldn't happen. The gravitational interactions between two stars orbiting each other would disrupt the protoplanetary disk, the swirling cloud of gas and dust from which planets form. Material in the disk would experience competing gravitational pulls, creating chaotic orbits, preventing the gradual accretion that builds planets. But Kepler 16b proved that intuition wrong. Not only can planets form in binary systems, they can form in relatively close binary systems, where the stars are just a fraction of an astronomical unit apart. The key seems to be that circumbinary planets form farther out, beyond a certain critical radius, where orbits become stable, where the two stars act more like a single, combined gravitational source than two competing influences. Since the discovery of Kepler 16b in 2011, astronomers have found more than a dozen other confirmed circumbinary planets. Each one adds to our understanding of how planetary systems can assemble in environments very different from our own single-star configuration. Some of these systems have planets in the habitable zone, the region where temperatures could allow liquid water to exist on a planet's surface. The idea of a world with two suns where life might evolve, where hypothetical organisms would consider binary stars as normal and single-star systems as odd, that's no longer science fiction. The discovery method for Kepler-16b was particularly clever. The planet was detected through transits, but not simple transits, across one star. Astronomers observed the system and noticed that both stars experienced brightness dips at irregular intervals. The pattern didn't match a simple eclipse scenario where two stars pass in front of each other. The timing and depth of the dips indicated a third body, the planet, transiting across first one star, then the other, then both simultaneously depending on the alignment. Here's a planet that looks like Earth from a distance. HD 1897333b has a beautiful deep blue colour, almost cobalt, reminiscent of our own planet when photographed from space. It's one of the few exoplanets where astronomers have actually determined the colour by measuring the light reflected from the planet's atmosphere. And at first glance, that blue hue suggests something familiar, something Earth-like, perhaps oceans, water, the conditions for life. Then you look closer at the data and realise this blue world, wow, is one of the most hostile environments ever discovered. HD 1897333b is located 64 light-years away in the constellation Vulpecula. It's another hot Jupiter, orbiting its star every 2.2 days at a distance of only 0.03 astronomical units. The proximity to its star heats the planet's atmosphere to temperatures exceeding 1000 degrees Celsius. At these temperatures, water cannot exist as liquid or even as vapor in the form we know it. Molecules break apart, chemistry becomes exotic, so if the blue color doesn't come from oceans, what causes it? The answer is silicate particles. The atmosphere of HD 1897333b contains clouds of tiny glass-like particles, silicate grains formed from minerals that have been vaporized by heat and then condensed into microscopic droplets. These particles scatter blue light more effectively than red light, similar to the Rayleigh scattering that makes Earth's sky blue, but taken to an extreme. The entire atmosphere takes on this deep azure hue. But it's not just the colour that makes this world remarkable. It's the wind. HD 1897333b has been measured to have winds exceeding 8,700 kilometers per hour, about 7 times the speed of sound on Earth. These are not isolated jet streams. They're planet-wide circulation patterns, supersonic atmospheric currents that wrap around the entire world, moving from the day side to the night side and back again in an endless howling cycle. Now combine those two facts, silicate particles in the atmosphere, supersonic winds. What you get is something that sounds like a nightmare, glass shards flying sideways at thousands of kilometers per hour. Imagine rain, but instead of water droplets, it's molten glass. Or rather, not even molten anymore by the time it's moving at those velocities. Solid or semi-solid silicate particles, each one microscopic but collectively forming a sandblaster storm of unimaginable violence. Anything exposed to this environment would be scoured, abraded, eroded down to nothing in moments. The detection of this sideways glass rain came from spectroscopic observations using the Hubble Space Telescope and later confirmed by other instruments. Astronomers measured the reflected light from HD 1897333b during different phases of its orbit, similar to how we see phases of the Moon. By comparing the light reflected when the planet was fully illuminated from our perspective versus partially illuminated, they could determine the scattering properties of the atmosphere and infer the presence of small reflective particles. The wind speeds were measured using a different technique. Astronomers observed the planet during transit, when it passes in front of its star from our viewpoint. By taking ultra-high resolution spectra of the starlight filtering through the edges of the planet's atmosphere, they could detect Doppler shifts in spectral lines caused by atmospheric motion. Material on one side of the planet moving toward us shifts spectral lines toward the blue. Material on the other side moving away shifts them toward the red. The magnitude of these shifts reveals the velocity, and the velocities detected were staggering, far exceeding anything measured in our solar system. HD 1189733b also experiences another phenomenon that would be devastating if it occurred on Earth: atmospheric stripping. The intense stellar wind from its nearby host star constantly bombards the upper atmosphere, blowing away material into space. Observations have detected a comet-like tail of hydrogen gas trailing behind the planet, material being lost at a rate of hundreds of thousands of tons per second. Over time, this process could erode away the entire atmosphere, leaving behind a stripped core, or perhaps just dispersing the planet completely. The blue colour that initially made HD 1189733b seem appealing is really a warning sign. It's the colour of a world where chemistry has gone wild, where physics operates at extremes, where beauty and lethality are inseparable. A world that from a distance might trigger a sense of familiarity, but up close would be instantly fatal. Most of the exoplanets we've discussed so far orbit living stars, stars that are fusing hydrogen into helium in their cores, generating energy, maintaining stable equilibrium. But not all planets are so fortunate. Some orbit the corpses of dead stars, and their stories are among the strangest in all of astronomy. Let's start at the beginning, with the very first exoplanets ever confirmed. Yes, before 51 Pegasi b, before the hot Jupiter revolution, there was another discovery, and it happened in one of the most unlikely places imaginable. In 1992, astronomers Alexander Wolszczan and Dale Frail announced the detection of two planets, later confirmed to be three planets, orbiting an object called PSR B1257+12. That designation might look cryptic, but it tells you exactly what kind of object we're dealing with. PSR stands for pulsar. A pulsar is a rapidly spinning neutron star, the collapsed core left behind after a massive star explodes as a supernova. Neutron stars are some of the most extreme objects in the universe. Take the mass of our Sun, about 2 times 10 to the 30th kilograms, and compress it into a sphere just 20 kilometers across. The density becomes so extreme that a teaspoonful of neutron star material would weigh about 1 billion tons on Earth. The gravity at the surface is so intense that the escape velocity approaches half the speed of light. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. As the star rotates, these beams sweep across space like a lighthouse. If Earth happens to be in the path of one of these beams, we see regular pulses of radio emission, arriving with clock-like precision. The pulsar at the center of this story, PSR B57+12, spins once every 6.22 milliseconds. That's 161 rotations per second, and the pulses from this pulsar arrive at Earth with such regularity that they rival atomic clocks in precision. But in 1990, Wolszczan noticed something odd. The pulses weren't perfectly regular. There were tiny variations in the arrival times, periodic shifts that repeated in patterns measured in months. After ruling out instrumental effects, Earth's orbital motion, and other sources of error, only one explanation fit the data. Something was orbiting the pulsar, and the gravitational influence of that something was causing the pulsar to wobble ever so slightly, changing the distance to Earth by small amounts and thus altering the arrival times of the pulses. By analysing the patterns in the timing variations, Wolszczan and Frail determined that not one, but at least 2 planets were orbiting PSR B257+12. Later observations confirmed a third planet and suggested the possible presence of a fourth. These worlds have masses in the range of Earth's mass and orbit at distances comparable to the inner solar system. They circle a dead star every few months, bathed in radiation from the pulsar's beams, existing in an environment utterly hostile to anything resembling life. The discovery was shocking for multiple reasons. First, it was the first confirmed detection of planets beyond our solar system, predating 51 Pegasi b by 3 years. Second, and more philosophically troubling, these planets shouldn't exist, at least not if you follow the conventional narrative of planet formation. Here's why. PSR B2257 plus 12 is a pulsar, which means it was once a massive star that went supernova. Supernova explosions are among the most violent events in the universe. They release as much energy in a few weeks as the Sun will emit over its entire 10 billion year lifetime. Any planets that existed around the star before it exploded should have been vaporized, blown away, or ejected from the system entirely. The shockwave alone would be devastating. The radiation flux would strip away atmospheres and melt surfaces. Nothing should survive. And yet here are 3 planets, orbiting peacefully around a pulsar. The only reasonable explanation is that these are second-generation planets. They formed after the supernova from the debris disk that remained, from material that didn't escape the system, but instead settled into orbit around the newly formed neutron star. This is planet formation under the most extreme conditions imaginable. Chemistry and accretion happening in a radiation-drenched, gravitationally tortured environment, producing worlds that have no analogues in our solar system. There's a planet in the constellation Cancer, orbiting a star called 55 Cancri, that captured the public imagination like few others. Headlines proclaimed it was made of diamond, a world where the surface glittered with crystalline carbon, where oceans of liquid graphite lapped against shores of compressed carbon lattices. The estimated value of such a world, if you could somehow mine it and bring it to Earth, was calculated to be orders of magnitude greater than the entire global economy. It was the ultimate treasure, a planetary jewel floating in space just 40 light years away. And like so many headlines, the reality is far more complicated and considerably less certain. 55 Cancri A, as the planet is formally designated, is a super-Earth orbiting very close to its star. It has about 8 times the mass of Earth and completes one orbit every 18 hours. Yes, 18 hours. The year on this planet is shorter than a single day on Earth. The proximity to its star heats the surface to temperatures exceeding 2000 degrees Celsius, hot enough to melt rock and vaporize most metals. The diamond hypothesis comes from early models of the planet's composition based on its density and the assumed composition of its parent star. Astronomers noted that 55 Cancri itself has an unusual chemical signature, with a higher ratio of carbon to oxygen compared to the Sun. In our solar system, oxygen is more abundant than carbon, which means that when rocky planets form, oxygen bonds with silicon to form silicates, the primary component of Earth's mantle and crust. Any leftover carbon ends up in smaller quantities. But if you flip that ratio, if carbon outnumbers oxygen, then the chemistry of planet formation changes dramatically. Carbon would be the dominant element, bonding with itself and with other elements to form carbon-rich minerals. Under the extreme pressures inside a planet, carbon can crystallize into diamond. So if 55 Cancri E formed from carbon-rich material, its interior and possibly its surface could contain vast quantities of diamond, perhaps comprising a significant fraction of the planet's mass. It was a beautiful hypothesis. It generated enormous public interest, and it was almost certainly wrong, or at least vastly oversimplified. More recent observations, particularly from the James Webb Space Telescope and the Spitzer Space Telescope, have painted a different picture. The atmosphere of 55 Cancri A, which can be studied by observing the planet during transit and analysing the starlight filtering through its upper atmosphere, shows evidence of carbon monoxide and carbon dioxide, suggesting a carbon-rich environment. But the presence of these gases also indicates that oxygen is still present in significant quantities. Furthermore, thermal observations of the planet's day and night sides reveal temperature variations that don't match what you'd expect for a solid diamond surface. Diamond is an excellent thermal conductor. A planet with a diamond crust should transport heat very efficiently from the day side to the night side, reducing temperature differences. But 55 Cancri E shows large temperature contrasts between hemispheres, suggesting a surface or atmosphere that doesn't conduct heat well. The current best guess, subject to change as more data arrives, is that 55 Cancri E is more likely a lava world, the extreme. Surface temperatures keep rock in a molten or semi-molten state. The atmosphere is thick with vaporized rock, silicates and carbon compounds in gaseous form, creating a hazy envelope that redistributes some, but not all of the stellar heat. There may be carbon-rich regions, possibly layers of graphite, or even small diamonds formed under pressure. But the idea of a glittering diamond planet has faded into the realm of oversimplification. This story illustrates one of the challenges of exoplanet science. We're studying worlds we can never visit, using indirect measurements, constructing models based on limited data. Early models make assumptions, often reasonable ones based on available information. But as technology improves and more observations accumulate, those models get revised, refined, and sometimes overturned completely. The lesson from 55 Cancri A is not that astronomers were wrong to propose the diamond planet idea. They were working with the best data and theories available at the time. The lesson is that the universe is more complex than our models, that simple narratives rarely capture the full reality, and that every answer in exoplanet science opens up 3 new questions. And honestly, a lava world with an atmosphere of vaporized rock is just as fascinating as a diamond planet, even if it doesn't make for as catchy a headline. If you think Saturn's rings are impressive, wait until you see J-Fo 7b. Saturn is famous for its ring system, arguably the most recognizable feature of any planet in our solar system. The rings extend from about 7,000 kilometers above Saturn's equator out to roughly 80,000 kilometers, spanning a distance of about 280,000 kilometers if you measure from edge to edge through the planet. That sounds enormous, and by terrestrial standards, it is. But in the grand scheme of planetary science, Saturn's rings are actually fairly modest. Now consider J-Fo 7b. This is not a confirmed exoplanet in the traditional sense because it's never been directly detected. But there is overwhelming indirect evidence for its existence, and that evidence comes from one of the most bizarre transit events ever observed. In 2012, astronomers monitoring the young star J-Fo 7 noticed something extraordinary. The star began to dim, not a quick dip like a normal planetary transit that lasts a few hours, not even an extended dimming like you might get from a large planet slowly crossing the stellar disk. This dimming event lasted for several weeks and showed a complex pattern of dips and recoveries, as if something with an intricate structure was passing between the star and Earth. By analysing the light curve, the graph of brightness over time, astronomers reconstructed what must have been blocking the star. The only model that fit the observations was an enormous ring system, far larger than anything in our solar system, orbiting around an unseen object. The ring system of J-Fo 7b, assuming that's what we observed, extends out to a radius of approximately 90 million kilometers. To put that in perspective, Earth orbits the Sun at a distance of 150 million kilometers. The rings of J-Fo 7b, if placed in our solar system, would stretch well beyond the orbit of Venus and nearly halfway to Earth. They're roughly 200 times larger in radius than Saturn's rings. The structure of these rings is complex. The light curve shows multiple dips of varying depth and duration, suggesting that the rings are not uniform, but instead contain gaps, dense regions, and perhaps shepherding moons, or embedded moonlets that create structure through gravitational interactions. There are hints of at least 37 distinct ring features, far more than the handful of major divisions in Saturn's rings. The object at the centre of this ring system, J1407b itself, is estimated to be between 10 and 40 times the mass of Jupiter. That puts it right at the boundary between a supermassive planet and a brown dwarf, objects that are too large to be called planets, but not quite massive enough to sustain hydrogen fusion and become stars. Whether J1407b is technically a planet or a substellar object is a matter of definition, but what's undeniable is that it possesses a ring system unlike anything else ever detected. One of the most intriguing features of the J1407b ring system is evidence of gaps where material has been cleared out. In Saturn's rings, gaps are typically created by the gravitational influence of moons orbiting within or near the rings. The moon Daphnis, for example, creates the Keeler gap in Saturn's A-ring through its gravitational pull. By analogy, the gaps in J1407b's rings suggest the presence of exomoons, moons orbiting this giant ringed planet, or ringed brown dwarf, sculpting and shaping the ring structure through their gravitational influence. If this interpretation is correct, then J1407b is not just a planet with rings. It's a mini-planetary system unto itself, a massive central body surrounded by a disk of material that may be in the process of forming moons, analogous to the way the early solar system's protoplanetary disk formed planets around the young Sun. The star J1407 is young, only about 16 million years old. For comparison, our Sun is 4.6 billion years old. At this early stage, planetary systems are still settling down, moons are still forming, ring systems are more common and more substantial because there hasn't been enough time for the material to coalesce into larger bodies or be swept away by gravitational interactions. Astronomers believe that Jupiter and Saturn may have had much more extensive ring systems in their youth, systems that gradually dissipated as moons formed and collisions redistributed material. If we're lucky, J1407b will transit its star again, allowing more detailed observations. But the orbital period is estimated to be roughly a decade or more, so we're still waiting for the next event. Not all planets orbit stars. Some drift through the dark emptiness of interstellar space, gravitationally unbound, solitary wanderers in the vast gulf between solar systems. These are the rogue planets, and they represent one of the most haunting categories of worlds in the known universe. The existence of rogue planets was predicted theoretically long before any were discovered. Planetary formation is a chaotic process. Young solar systems are crowded, unstable places where newly formed planets jostle for position, their orbits shifting due to gravitational interactions. Sometimes these interactions result in one planet being ejected entirely, flung out of the system at velocities high enough to escape the star's gravity. Once ejected, the planet becomes a wanderer, drifting through the galaxy for billions of years, moving through the dark with no sun to warm it, no stellar light to illuminate its surface. Detecting rogue planets is extraordinarily difficult. They emit no light of their own beyond faint infrared radiation from residual heat. They don't transit stars because they're not orbiting stars. They don't cause radial velocity wobbles. The only reliable method for finding them is gravitational microlensing, which requires a rogue planet to pass almost directly between Earth and a background star, an alignment that happens rarely and unpredictably. Despite these challenges, astronomers have confirmed several rogue planets and identified many more candidates. One of the most intriguing is CFBD SIR 21490403, an object discovered in 2012 floating about 130 light-years from Earth. Initial estimates suggested it might be between 50 and 120 million years old, and about 4 to 7 times the mass of Jupiter. The object is not orbiting any star, though it may be loosely associated with a moving group of young stars called the AB Doradus moving group, suggesting it may have been ejected from one of those systems in the distant past. Another candidate, PSO J318522, discovered in 2013, is even more mysterious. It has a mass about 6 times that of Jupiter and is only about 12 million years old. What makes it remarkable is its isolation. It's not near any star, not associated with any stellar group. It's just out there, alone, glowing faintly in infrared light due to heat left over from its formation. The question that keeps astronomers up at night is how many of these rogue planets are out there. Current estimates, based on microlensing surveys and theoretical models of planetary system formation, suggest there could be billions of rogue planets in the Milky Way galaxy. Some estimates push that number even higher, suggesting there might be more rogue planets than stars, possibly trillions of these dark worlds drifting silently through the interstellar void. Think about that for a moment. Trillions of planets, each one perhaps as large as Earth or Jupiter, scattered across the galaxy. With no home system, no star to orbit, worlds that formed around a sun, possibly even harboured atmospheres and geologic activity before being ejected into the cold and dark. If any of these planets once had life, that life would have been extinguished quickly as temperatures plummeted, atmospheres froze, and energy sources vanished. But here's a strange possibility that some scientists have considered. Could a rogue planet retain enough internal heat to maintain liquid water beneath an ice-covered surface? Earth's oceans are heated primarily by the sun, but there are examples in our own solar system of moons that maintain subsurface oceans through tidal heating and radiogenic decay. Europa, Enceladus, and possibly other moons of Jupiter and Saturn have liquid water oceans beneath thick ice shells, kept from freezing by the heat generated from radioactive decay in their cores and from tidal flexing caused by their host planets. A rogue planet, especially a large one, could retain heat for billions of years through radioactive decay alone. If it had a thick ice crust acting as insulation, it's theoretically possible, though unlikely, that a subsurface ocean could persist. Such an ocean would be completely dark, cut off from any star's energy, but life on Earth has shown that sunlight is not strictly necessary. Deep-sea hydrothermal vents host entire ecosystems based on chemosynthesis, life that derives energy from chemical reactions rather than photosynthesis. Could similar ecosystems exist beneath the ice of a rogue planet? It's a long shot. The energy budget would be minimal. The environment would be incredibly harsh. But it's not impossible. And in a galaxy with trillions of rogue planets, even a low probability event becomes statistically likely somewhere. Let's turn our attention now to a class of planets that exist at the very edge of what we can call a planet at all, the ultra-short period planets, worlds that orbit so close to their stars that their surfaces are oceans of molten rock. Kepler 78b is the poster child for this category. This planet is only slightly larger than Earth, about 1.2 times Earth's radius and 1.7 times Earth's mass, making it one of the most Earth-like exoplanets in terms of size and density. But that's where the similarities end. Kepler 78b orbits its star every 8.5 hours. Not 8.5 days, 8.5 hours. A year on this planet is shorter than a work shift. At that distance, roughly 900,000 kilometers from its star, the surface temperature is estimated to exceed 2,500 degrees Celsius. That's hot enough to vaporize rock. The day side of Kepler 78b is almost certainly covered in a magma ocean, liquid rock churning and convecting under the intense stellar radiation. The night side, though still incredibly hot, by any reasonable standard, might be cool enough for rock to partially solidify into a thin crust, only to be melted again as rotation brings it back around to face the star. The existence of planets like Kepler 78b raises a fundamental question that planetary scientists are still grappling with. How did they get there? Planets don't form that close to their stars, the protoplanetary disk, the cloud of gas and dust from which planets assemble, is too hot near the star for solid material to condense. Rock and metal vaporize. There's nothing solid to build a planet from. The rocky planets in our solar system formed farther out where temperatures were low enough for materials to remain solid. And even our closest planet, Mercury, orbits at a comfortable distance compared to these ultra-short period worlds. The only explanation is migration. Kepler 78b must have formed much farther out in the protoplanetary disk and then spiraled inward over time. But here's the problem. We don't have a good theoretical framework for how a planet could migrate that far inward and then stop, stabilizing in an ultra-short orbit. Most migration mechanisms, such as tidal interactions with the protoplanetary disk or gravitational scattering by other planets, predict that a planet migrating inward should continue migrating until it falls into the star. There's no obvious brake mechanism. So why is Kepler 78b still there? One hypothesis is that we're catching these planets in the act of dying. They're spiraling inward, losing orbital energy through tidal interactions with the star, and they will eventually be consumed. The timescale for this process is uncertain, possibly millions of years, possibly much longer, but the ultimate fate is sealed. We're seeing these planets in a transient phase, the last stage of their existence before annihilation. Another lava world, K2141b, offers even more extreme conditions. This planet orbits its star every 6.7 hours and is tidally locked with the day side permanently facing the star. Surface temperatures on the day side reach 3000 degrees Celsius, hot enough to vaporize not just water or iron, but rock itself. Sodium, silicon monoxide and silicon dioxide, the primary components of rock-forming minerals, exist as vapors in the atmosphere above the magma ocean. Atmospheric modeling suggests that K2141b might have a weather cycle involving rock vapor. On the day side, rock vaporizes into the atmosphere. Supersonic winds carry this vapor to the night side, where temperatures drop enough for it to condense and rain back down as molten rock. The magma flows back toward the day side through subsurface convection, completing the cycle. It's a rock cycle analogous to the water cycle on Earth, but with liquid and vaporized rock instead of liquid and gaseous water. Imagine standing on the night side of K2141b if you could somehow survive the heat. The sky above would be hazy with rock vapor. Droplets of molten silicon compounds would fall from the clouds. Jill continue owing as they descended toward the molten surface. The horizon would glow with a dull red light from the day side, and the air itself, composed of vaporized minerals, would be thick enough to see, a shimmering haze that distorts everything beyond a few meters. These lava worlds are laboratories for understanding planetary physics. Under extreme conditions, they tell us about material properties at temperatures we can barely reproduce in laboratories on Earth. They reveal atmospheric dynamics involving substances we normally think of as solid, and they force us to expand our definition of what qualifies as an atmosphere. If rock vapor can form clouds and precipitation cycles, then the boundary between surface and atmosphere becomes blurred in ways that don't occur on Earth. Now let's shift from fire to water and explore a type of planet that might be common in the galaxy, but remains difficult to confirm: the ocean world. Earth is sometimes called a water world because 70% of its surface is covered by oceans. But Earth's oceans are actually quite shallow compared to the planet's overall size. If you took all the water on Earth and formed it into a sphere, that sphere would be only about 1,400 kilometers in diameter. Earth itself is 12,742 kilometers in diameter. Water represents only about 0.02% of Earth's total mass. We're not really a water world, we're a rocky planet with some water on top. True water worlds, if they exist, would be planets where water comprises a significant fraction of the total mass, perhaps 20 or 30%. These worlds would have global oceans hundreds or even thousands of kilometers deep, with no land whatsoever breaking the surface. Beneath the ocean, instead of reaching a rocky ocean floor like on Earth, you would eventually encounter layers of exotic high-pressure ices, water compressed into crystal structures that remain solid even at relatively high temperatures due to the extreme pressure. Several exoplanets have been identified as potential water worlds based on their size, density, and the composition of their parent stars. Kepler 22b, discovered in 2011, was one of the first exoplanets confirmed to orbit in the habitable zone of a Sun-like star. It's about 2.4 times Earth's radius and orbits its star every 290 days. The planet's density, estimated from its mass and radius, is lower than Earth's, suggesting it could be composed of a rocky core surrounded by a massive water envelope. But here's the challenge: we can't actually see the surface or measure the composition directly. The density measurement tells us the planet is less dense than pure rock, but doesn't tell us whether that's because of water, hydrogen, and helium gas, or some other low-density material. Kepler 22b could be a water world. It could also be a mini Neptune with a thick hydrogen atmosphere. Or it could be something we haven't even imagined yet. The data is consistent with multiple interpretations. Another candidate, K2-18b, has generated enormous excitement and controversy. This planet orbits in the habitable zone of a red dwarf star, about 120 light-years away. It's about 2.6 times Earth's radius and roughly 8.6 times Earth's mass. In 2019, astronomers announced the detection of water vapor in its atmosphere using observations from the Hubble Space Telescope. Later observations with the James Webb Space Telescope in 2023 and 2024 detected not just water vapor, but also carbon dioxide and methane. The presence of methane is particularly intriguing because on Earth, methane in the atmosphere is often associated with biological processes. Microbes produce methane as a metabolic byproduct. Wetlands, rice paddies, and the digestive systems of animals all release methane into Earth's atmosphere. Could the methane on K2-18b be a biosignature, evidence of life? The scientific community is deeply divided on this question. Some researchers argue that the combination of water vapor, carbon dioxide, and methane is exactly what you'd expect from a habitable ocean world with biological activity. Others point out that methane can also be produced by non-biological processes, such as reactions between water and rock at high temperatures, or by chemistry in a hydrogen-rich atmosphere. Extraordinary claims require extraordinary evidence, and the detection of methane alone is not sufficient proof of life. Further complicating the picture is the question of whether K2-18b is actually habitable. The planet orbits a red dwarf star, which means it's likely subjected to intense stellar flares and high-energy radiation. Red dwarfs are magnetically active stars, prone to sudden explosive events that could strip away a planet's atmosphere or sterilize its surface with radiation. Even if K2-18b has liquid water and a thick atmosphere, the environment might be too hostile for life as we know it. Then there's the issue of the planet's internal structure. If K2-18b is truly a water world, with a global ocean hundreds of kilometers deep, the pressure at the bottom of that ocean would be immense. Water under those conditions would freeze into exotic ice phases, forming a solid layer between the liquid ocean and the rocky core. This ice layer could prevent the geochemical cycling that on Earth helps regulate atmospheric composition and provides nutrients essential for life. Without plate tectonics, without volcanic activity to release gases into the ocean and atmosphere, a deep water world might be geologically dead, stable but sterile. Here's a category of exoplanets that defies easy explanation. The super-puffed planets, worlds with densities so low they're sometimes called cotton candy planets. WASP 107b is the perfect example. This planet has a mass of about 0.1 of Jupiter masses, roughly 1/10 the mass of Jupiter, but its radius is 0.94 Jupiter radii, almost as large as Jupiter itself. Do the math on that density, and you get about 0.13 grams per cubic centimeter. For comparison, Jupiter's density is 1.33 grams per cubic centimeter. Earth's density is 5.51 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. WASP 107b is less dense than water. It's less dense than cork. It's approaching the density of cotton candy or styrofoam. How is that possible? A planet is held together by gravity. The more massive a planet, the stronger its gravity, the more it can compress its own material. Jupiter is mostly hydrogen and helium, the two lightest elements, but it's still fairly dense because its own gravity compresses that gas significantly. To have a planet nearly as large as Jupiter, but only 1/10 the mass means that planet is not compressed at all. Its gravity is too weak to squeeze its atmosphere. The gas just puffs out into a huge extended envelope. But this raises a fundamental problem. Where did all that gas come from? And why hasn't it escaped into space? Gas giants form by first building up a solid core of rock and ice, typically at least 10 times Earth's mass. Once that core reaches a critical mass, it can gravitationally capture and hold onto hydrogen and helium gas from the surrounding protoplanetary disk. The core acts as the gravitational anchor that keeps the atmosphere bound. But WASP 107b doesn't have enough total mass to have built a substantial core and still have room for all that atmosphere. The core must be small, perhaps only a few Earth masses at most. With such a small core and such a huge extended atmosphere, the planet's gravity at the top of the atmosphere is very weak. Atmospheric particles there are barely bound to the planet. They should be escaping into space constantly, blown away by stellar wind, heated by the star's radiation until they achieve escape velocity. A planet like WASP 107b shouldn't be able to retain its atmosphere over long timescales. And yet there it is, puffy and stable, orbiting its star every 5.7 days. One hypothesis is that we're seeing these planets during a brief, transient phase. They formed with larger atmospheres and are in the process of losing that gas. In another few 100 million years, WASP 107b might shrink down to a much smaller radius as its atmosphere escapes, eventually leaving behind just the small rocky core. We happen to be observing it during the inflated phase. Another possibility involves internal heating. If the planet's interior is significantly warmer than models predict, either from residual heat from formation or from tidal heating caused by its orbit, that internal heat could puff up the atmosphere, keeping it extended despite the weak gravity. Some models suggest that ongoing tidal dissipation, the conversion of orbital energy into heat through tidal flexing, could provide enough energy to maintain the puffed up state. WASP 107b is not unique. Several other super-puffed planets have been discovered, including Kepler 51b, Kepler 51c, and Kepler 51d, a system of 3 ultra-low-density planets, all orbiting the same star. The Kepler 51 planets are even less dense than WASP 107b, with densities around 0.03 grams per cubic centimeter. They're among the least dense objects ever discovered that are massive enough to be called planets. The atmospheres of these puffy planets are incredibly difficult to study because they're so extended and diffuse. When our astronomers try to take spectra during transits, the signals are weak and contaminated by stellar activity. But the limited data available suggests that these atmospheres might be rich in hydrogen and helium, as expected, but also possibly contain significant amounts of water vapor and methane, giving them a hazy appearance that further complicates spectroscopic analysis. One of the most intriguing questions about super-puffed planets is whether they represent a common phase in planetary evolution, or whether they require special conditions to form. If they're transient, then most planetary systems might host puffy planets at some point, but only for a cosmologically brief period. If they require specific formation scenarios, such as forming far from the star, where ice can contribute to the core mass and then migrating inward, they might be relatively rare. The discovery of multiple examples in the Kepler-51 system suggests they're not one-off flukes. There might be physical conditions that favour their formation and allow them to persist longer than simple models predict. Most planets in our solar system orbit the Sun in nearly circular paths. Earth's orbit has an eccentricity of 0.017, meaning it's almost perfectly circular. Even Mercury, the most eccentric planet in our solar system, has an eccentricity of only 0.21. This circular or near-circular orbital pattern is what astronomers expected to find around other stars, because circular orbits are generally more stable and are the natural outcome of angular momentum conservation during planet formation. Then we started discovering exoplanets, and we found that many of them have wildly eccentric orbits, stretching into elongated ellipses that bring them very close to their stars at one point in their orbit, and then swing them far away at another point. HD 80606b holds the record for one of the most eccentric orbits ever discovered for a planet. This gas giant, slightly smaller than Jupiter, orbits its star with an eccentricity of 0.93. To understand what that means, imagine an orbit so stretched that the planet's distance from its star varies by a factor of 10 over the course of a single orbit. At Periastron, the closest approach, HD 80606, comes within 0.03 astronomical units of its star. At Apastron, the farthest point, it swings out to 0.88 astronomical units. The orbital period is 111 days. For most of that time, the planet is relatively far from its star, experiencing temperatures comparable to Venus or Earth. Then, over the course of just a few hours, it plunges toward the star, passing through the region where temperatures skyrocket before swinging back out again. At Periastron, the stellar radiation flux increases by a factor of more than 800 compared to Apastron. The effects of this on the planet's atmosphere are catastrophic and fascinating. As HD 80606b approaches Periastron, the intense radiation heats the dayside atmosphere to temperatures exceeding Sun 200 degrees Celsius in a matter of hours. The rapid heating drives supersonic shockwaves through the atmosphere, compressing gas, triggering massive storms, creating global atmospheric upheaval. Then, just as quickly, the planet swings back out, and the atmosphere begins to cool and settle. Observations of HD 80606b during its Periastron passage, using the Spitzer Space Telescope, captured this thermal rollercoaster in real time. Astronomers watched the planet's infrared brightness increase dramatically as it heated up, then gradually decline as it moved away from the star. The data showed that the atmosphere responds to the heating on timescales of hours, far faster than the multi-day response times seen in planets with circular orbits. What causes these eccentric orbits? In our solar system, the leading theory is that the planets formed in initially eccentric orbits, but gradually circularized due to tidal interactions with the protoplanetary disk and with each other. For exoplanets, especially those in highly eccentric orbits, something must have disrupted this circularization process. The most likely culprit is gravitational interactions with other planets or with stellar companions. In a multi-planet system, if two planets come too close, their gravitational interaction can fling one into an eccentric orbit, while either ejecting the other planet entirely or sending it into its own disturbed orbit. Similarly, if a planetary system exists in a binary star system, the gravitational influence of the second star can perturb planetary orbits, pumping up their eccentricities. HD 80606 is actually part of a binary star system. The planet orbits one of the stars, HD 80606a, but there's a second star, HD 80606b, orbiting at a distance of about 200 astronomical units. The gravitational influence of this distant companion, combined with something called the Kozai mechanism, where the orbital plane of the planet precesses due to the binary companion, can drive the planet into a highly eccentric orbit over millions of years. Another planet with a remarkable orbit is HD 20782b, which has an eccentricity of 0.97, even higher than HD 80606b. This planet's orbit takes it from 0.06 astronomical units at periastron to 2.5 astronomical units at apastron. The variation in stellar heating is so extreme that the planet experiences seasons unlike anything in our solar system. Not seasons caused by axial tilt like Earth, but seasons caused by changing distance from the star. Seasons where temperatures rise and fall by thousands of degrees over the course of months. Eccentric orbits have profound implications for habitability. A planet in a highly eccentric orbit might spend most of its time too cold for liquid water and only briefly pass through the habitable zone during periastron. Any life trying to evolve on such a world would have to cope with wildly varying temperatures, radiation levels, and atmospheric conditions. Let's return to hot Jupiters for a moment, but with a specific focus on a subset that has puzzled astronomers for years: the inflated hot Jupiters, planets that are significantly larger than they should be, based on standard models of planetary structure. WASP 121b is one of the most extreme examples. This planet has a mass of about 1.18 Jupiter masses, but a radius of 1.87 Jupiter radii. That makes it nearly twice as large as Jupiter, despite being only slightly more massive. The density is absurdly low, and according to every standard model of gas giant structure, a planet with that mass should have collapsed under its own gravity into a much smaller radius. So why is it so bloated? The planet orbits its star every 1.3 days, at a distance of only 0.025 astronomical units. At that proximity, the stellar radiation is intense, heating the atmosphere to temperatures exceeding 2,500 degrees Celsius. The day side is hot enough to vaporize iron, titanium, and other metals. In fact, spectroscopic observations have detected gaseous iron and titanium in the upper atmosphere, along with water vapor in a high-altitude haze. The leading theory for the inflation involves energy deposition deep in the planet's atmosphere. Here's the basic idea: stellar radiation, particularly in the form of high-energy ultraviolet and X-ray photons, penetrates into the upper atmosphere and gets absorbed. Normally, this absorbed energy would be radiated back into space as infrared light, maintaining thermal equilibrium. But if some mechanism transports that energy downward into the deeper atmosphere faster than it can be radiated away, the interior of the planet heats up, causing the gas to expand. This downward energy transport could happen through several mechanisms. One possibility is atmospheric circulation, where hot gas from the upper atmosphere mixes downward through convection or advection. Another involves the absorption of stellar radiation by specific molecules or atoms, such as titanium oxide or metal atoms, which then transfer that energy to surrounding gas molecules through collisions. But there's a problem with this theory. The numbers don't quite add up. When astronomers calculate how much energy is being deposited by stellar radiation and compare it to the amount of inflation observed, the observed inflation is too large. Something else must be contributing additional energy. One hypothesis involves tidal heating. Even though WASP 121b is in a close orbit, it's not quite perfectly circular, and it's not quite perfectly tidally locked. The slight eccentricity of the orbit and any small deviation from perfect tidal locking would cause tidal flexing, where the planet gets squeezed and stretched by varying gravitational forces as it orbits. This flexing generates heat through friction, similar to how kneading dough warms it up. For WASP 121b, tidal heating could be depositing significant energy into the planet's interior, contributing to the inflation. Another possibility is magnetic induction heating. If the planet has a magnetic field and it's orbiting through the star's magnetic field, electric currents can be induced in the planet's interior. These currents encounter resistance, generating heat. This mechanism has been proposed for several inflated hot Jupiters, but the amount of heating depends on the strength of both the planetary and stellar magnetic fields, neither of which we can measure directly for most exoplanets. WASP 121b is so close to its star and so tidally stretched that it's actually being torn apart. The planet is egg-shaped, elongated toward the star due to tidal forces. Observations suggest that the planet is losing mass, with material being stripped from the outer atmosphere and either falling onto the star or escaping into space. The planet is slowly evaporating, and in a few million years, it might be destroyed completely, either consumed by the star or reduced to a much smaller rocky core. Another extremely inflated hot Jupiter is WASP 17b, which has a radius of about 1.99 Jupiter radii, making it one of the largest known exoplanets. What makes WASP 17b even more unusual is that it appears to be orbiting its star in the opposite direction to the star's rotation, a retrograde orbit. This suggests a violent history involving gravitational interactions that not only puffed up the planet, but also flipped its orbit. The mystery of inflated hot Jupiters remains one of the outstanding puzzles in exoplanet science. We have multiple plausible mechanisms that could contribute to inflation, but we don't have a definitive answer for which mechanism dominates or whether multiple mechanisms are working together. Each inflated planet might have its own unique combination of factors, making it difficult to construct a unified theory that explains them all. We've spent a lot of time discussing hot planets, worlds baking under intense stellar radiation. Now let's swing to the opposite extreme and talk about the frozen worlds, planets that exist at the outer edges of their solar systems or beyond, where temperatures plummet to near absolute zero. Ogil 2016 BLG or 1195 Lb is one of the coldest exoplanets ever discovered. Detected through gravitational microlensing, this planet is roughly Earth's mass and orbits its star at a distance similar to the distance between the Sun and Uranus or Neptune. But its star is not like the Sun. It's an ultra-cool dwarf, possibly even a brown dwarf, emitting very little light and heat. As a result, the surface temperature of Ogil 2016 BLG on 1195 Lb is estimated to be around -220 degrees Celsius, cold enough for nitrogen, oxygen, and carbon dioxide to freeze solid. This is not a world with liquid water oceans or even frozen water glaciers. Water at these temperatures is harder than steel. The atmosphere, if one exists at all, would be composed of exotic ices or perhaps just a tenuous layer of sublimating gases that immediately refreeze and fall back to the surface. There would be no weather in any conventional sense, no wind-driven erosion, no active geology. Just a frozen ball of ice and rock locked in eternal cold, orbiting a dim star that provides almost no warmth. The discovery of Ogil 2016 BLG on 1195 Lb and similar cold planets raises an interesting question about the outer limits of planetary habitability. On Earth, life has been found in some of the most extreme cold environments imaginable. Microbes survive in Antarctic ice in permafrost that has been frozen for hundreds of thousands of years, even in glacier ice where temperatures never rise above freezing. These organisms have evolved antifreeze proteins, slow metabolic rates, and the ability to enter dormant states for extended periods. But there's a limit. Liquid water is essential for life as we know it. Without liquid water, biochemistry as we understand it cannot function. Molecules can't dissolve, can't diffuse, can't react. Everything grinds to a halt. Ogle, 2016, BLG 95 lb is far below the freezing point of water, even accounting for pressure or salt content that might depress the freezing point. However, some scientists have speculated about alternative biochemistries that might function in extremely cold environments using liquids other than water. Ammonia, for example, remains liquid at temperatures as low as -77 degrees Celsius at standard pressure. Methane and ethane, the substances that form lakes and seas on Saturn's moon Titan, are liquid at temperatures around -180 degrees Celsius. Could life evolve using these substances as solvents instead of water? It's speculative, highly uncertain, and probably unlikely. But it's not impossible, and in a galaxy with hundreds of billions of planets, even unlikely scenarios might occur somewhere. Another category of frozen worlds includes the planets orbiting in the habitable zones of red dwarf stars at distances where temperatures should allow liquid water, but where tidal locking creates extreme conditions. Proxima Centauri b, the closest known exoplanet to Earth at just 4.2 light-years away, orbits in the habitable zone of Proxima Centauri, a red dwarf star. The planet is probably tidally locked, meaning one side always faces the star, while the other side faces away into eternal darkness. If Proxima Centauri b has no atmosphere, or only a thin atmosphere, the night side would be frozen solid, possibly colder than any place in our solar system, except the most distant regions beyond Neptune. All the atmosphere, if there is one, might freeze out onto the night side, leaving the day side exposed to vacuum and intense stellar flares. The planet would be a split world, one hemisphere of fire, one of ice, with perhaps a narrow twilight zone in between where temperatures might briefly allow liquid water. But if Proxima Centauri b has a thick atmosphere, heat could be transported from the day side to the night side through atmospheric circulation, preventing the freeze-out and allowing a more moderate climate across the entire planet. Whether such an atmosphere exists and can survive. The intense stellar activity of Proxima Centauri is one of the key questions driving current research into this system. In 2019, astronomers announced the discovery of something completely unexpected, a planet apparently losing its hydrogen atmosphere and transforming into a helium-rich world. The planet is called GJ3470b, and it represents a potential new class of exoplanets that don't exist in our solar system. GJ3472b is a Neptune-sized planet orbiting a red dwarf star about 96 light-years away. With a mass about 14 times Earth's and a radius about 4 times Earth's, it's less dense than Neptune, suggesting a thick hydrogen and helium atmosphere surrounding a rocky or icy core. Initially, it seemed like a fairly typical warm Neptune, planets that are common in exoplanet surveys but absent from our own solar system. But observations with the Hubble Space Telescope revealed something unusual. The planet is losing its atmosphere at an extraordinary rate, shedding about 10,000 tons of material per second. That might not sound like much compared to the planet's total mass, but over geological timescales, this rate of atmospheric loss can strip away a significant fraction of the atmosphere. Here's what makes it remarkable. The escaping atmosphere is predominantly hydrogen. Helium, being a heavier atom, escapes more slowly. Over time, as hydrogen preferentially escapes into space, the atmosphere becomes progressively enriched in helium. Eventually, after hundreds of millions of years of this preferential loss, GJ3470b might end up with an atmosphere composed primarily of helium, a composition that doesn't occur naturally during planet formation. This discovery suggests the existence of a pathway for creating helium-rich planets through atmospheric stripping. It also provides a potential explanation for a puzzling gap in the exoplanet radius distribution called the Fulton Gap or the Radius Valley. Surveys have found that planets with radii between about 1.5 and 2 times Earth's radius are relatively rare. There are lots of super-Earths, smaller than 1.5 Earth radii, and lots of mini-Neptunes, larger than 2 Earth radii, but a deficit in between. The leading explanation for this gap is atmospheric loss. Mini-Neptunes that form with thick hydrogen and helium atmospheres gradually lose those atmospheres due to stellar radiation and stellar wind, particularly if they orbit close to their stars. As the atmosphere escapes, the planet shrinks, but the process doesn't create a smooth continuum of sizes. Instead, planets either retain most of their atmospheres and remain large, or they lose their atmospheres completely and shrink down to the underlying rocky core. This bimodal outcome creates a gap in the size distribution. GJ3470b might be caught in the middle of this transition, a planet actively losing its hydrogen atmosphere. If the helium escapes more slowly, the planet might stabilize with a helium-dominated atmosphere, filling in the radius gap with a new type of world. Detecting helium in exoplanet atmospheres is technically challenging, but increasingly feasible with modern instruments. Helium has a specific spectral line in the infrared, around 1.083 micrometers, that can be observed during transits. Several exoplanets have now been confirmed to have helium in their upper atmospheres, including WASP-1007b and HAT-P11b, providing observational support for the helium enrichment scenario. Another way to create helium-rich worlds involves something called hot super-Earths, or ultra-short period planets, like those we discussed earlier. If these planets lose their hydrogen atmospheres completely due to their proximity to their stars, but retain a thin envelope of heavier volatiles including helium, they might also end up helium-enriched. The existence of helium planets would have implications for understanding planetary evolution and the long-term fate of mini-Neptunes. It would mean that the exoplanet population includes not just planets in their initial formation states, but also planets that have been heavily modified by interactions with their host stars. Planets whose current compositions and structures are the result of billions of years of atmospheric erosion and chemical evolution. We're still in the early stages of characterizing these potential helium worlds. Most of the evidence is indirect, inferred from atmospheric loss rates and spectroscopic detections of helium signatures. To confirm the existence of a truly helium-dominated atmosphere would require detailed spectroscopy across multiple wavelengths, measuring not just the presence of helium, but also the absence or near absence of hydrogen and other lighter elements. As instruments improve, particularly with the James Webb Space Telescope's capabilities for transmission spectroscopy, we should be able to characterize these atmospheres in much more detail and determine whether helium planets are a real and significant population. Some planets are not content to simply orbit their stars in stable configurations. They're actively falling apart, shedding material into space, leaving trails of debris behind them as they slowly disintegrate. These are among the most dramatic and short-lived phenomena in exoplanet science. K222b, also known as KIC 57548b, was one of the first disintegrating planets ever discovered. It orbits its star every 15.7 hours, one of the shortest orbital periods known. But what made it immediately unusual was the transit signal. Instead of a clean, symmetric dip in the star's brightness as the planet passed in front, the transit showed an irregular, variable depth, sometimes blocking more starlight, sometimes less, and displaying a distinct asymmetry with a longer dimming tail following the planet. The explanation became clear once astronomers analysed the pattern. The planet is surrounded by a cloud of dusty material, and that cloud is being blown away from the planet like the tail of a comet. The planet itself is evaporating, losing mass to space at an estimated rate of 140,000 tons per second. The escaping material forms a trailing cloud that extends behind the planet in its orbit, and the density and distribution of this cloud varies over time, causing the irregular transit depths. The composition of the escaping material appears to be rocky rather than gaseous. Spectroscopic observations suggest the presence of dust particles made from rock-forming minerals, possibly silicates or metal oxides. This means K2-22b is not losing a gaseous hydrogen atmosphere like GJ347b. It's losing the actual rocky body of the planet itself, vaporized by intense stellar radiation at temperatures exceeding 2000 degrees Celsius. The planet is probably not very massive anymore. Estimates suggest it might have only a fraction of Earth's mass remaining, possibly as little as 0.1 Earth masses, making it more like a large asteroid than a proper planet. It won't last long by astronomical standards. At the current rate of mass loss, the planet could be completely destroyed within a few 100 million years, possibly less. Several other disintegrating planets have been discovered since K2-22b, including K2-22c, KIC 8639908b, and others. They share common characteristics: ultra-short orbital periods, high stellar radiation flux, evidence of dusty tails, and variable transit depths. They represent the endpoint of planetary migration and evolution, worlds that spiral too close to their stars and are now paying the ultimate price. One of the most intriguing aspects of these disintegrating planets is what they might become. As the outer layers evaporate, denser inner material becomes exposed. If the planet originally had an iron core, that core might survive longer than the surrounding rock, eventually leaving behind a tiny dense remnant, perhaps something similar to Mercury, but even more extreme. Or the planet might vanish entirely, dispersed into space, leaving only a faint ring of debris orbiting the star as evidence it ever existed. The discovery of disintegrating planets also provides a window into planetary interiors. On Earth, we can study our planet's interior only through indirect methods like seismology and by analysing volcanic rocks that originated deep underground. We can't directly sample the core or mantle, but when a planet disintegrates, it exposes its interior material directly. By analysing the composition of the escaping dust, astronomers can determine what the planet is made of at different depths, effectively getting a cross-section through a planetary interior. For K2-22b, the data suggest a composition rich in calcium, aluminum, and silicates, materials that on Earth would be found in the mantle rather than the crust. This implies the outer layers have already been stripped away, and we're seeing deeper material being exposed and vaporized. There's something almost melancholic about disintegrating planets. They're dying in real time, on timescales short enough that a human watching over a lifetime might notice measurable changes in the transit depths as the planet loses mass and the dust cloud evolves. In the grand timescale of the universe, these are brief flashes, transient phenomena that exist for only a cosmic moment before disappearing. But while they last, they provide invaluable insights into planetary composition, atmospheric loss, and the extreme physics of matter under intense thermal and radiative stress. They also serve as reminders that planets are not eternal. They form, evolve, and sometimes die, and the universe is full of processes that can destroy worlds as surely as it creates them. Throughout this journey, we've encountered many planets that challenge our understanding of planetary science. But some exoplanets are so bizarre, so contrary to theoretical predictions, that their very existence forces us to reconsider fundamental assumptions about how planetary systems form and evolve. WASP-18b is one of these. This planet has about 10 times the mass of Jupiter, making it one of the most massive planets ever discovered, right at the boundary between planet and brown dwarf. It orbits its star every 23 hours at a distance of only 0.02 astronomical units. That proximity combined with that mass creates an extreme tidal interaction between the planet and the star. Tidal forces work both ways. Just as the star's gravity raises tidal bulges on the planet's gravity raises tidal bulges on the star. These bulges don't align perfectly with the line connecting the two bodies because rotation and orbital motion cause a slight lag. This misalignment creates a torque that transfers angular momentum between the orbit and the star's rotation. For most planets, this process happens very slowly and has minimal effect over the system's lifetime. But WASP-18b is so massive and so close that the tidal interaction is extraordinarily strong. Calculations suggest that the planet is causing the star to slow down its rotation, while the planet itself is spiraling inward, losing orbital energy. The predicted timescale for the planet to fall into the star is only about 650,000 years. That's nothing in astronomical terms, a blink of an eye. The star is several billion years old. The planetary system has existed for most of that time. So why are we seeing WASP-18b now, in this brief final phase before destruction? The probability of randomly observing a planet during such a short-lived state is incredibly low. It's like seeing a snowflake at the exact moment it melts, when snowflakes might last for hours or days before melting. The most likely explanation is that the theoretical predictions are wrong. Perhaps tidal dissipation in the star is less efficient than models assume, which would extend the infall timescale to tens of millions or even hundreds of millions of years, making it much more plausible to observe. Or perhaps there's some mechanism that temporarily halts or reverses the infall, allowing the planet to survive longer than naive calculations suggest. WASP-18b is not unique in this regard. Several ultra-short period massive planets have been discovered with similar predicted short lifetimes. Collectively, they suggest that either tidal theory needs refinement or there's something happening in these extreme systems that we don't yet understand. Another planet that challenges theory is HD 106906b. This gas giant has a mass about 11 times Jupiter's and orbits its host star at a distance of 738 astronomical units. For reference, Neptune orbits the Sun at 30 astronomical units. Pluto averages about 39 astronomical units. HD 106906b is 20 times farther from its star than Pluto is from the Sun. At that distance, planet formation through core accretion, the standard model where planets build up gradually from colliding dust and rock, should be impossible. The material in the protoplanetary disk is too sparse, the orbital periods are too long, and the time required to accumulate enough mass to form a giant planet exceeds the lifetime of the disk itself. The alternative explanation is that HD 106906b formed through gravitational instability, where a dense region of the protoplanetary disk collapsed directly into a planet without going through the slow accumulation process. But gravitational instability typically produces brown dwarfs, or very massive planets, and it's unclear whether it can form objects at the lower end of the mass range, where HD 106906b sits. There's another mystery. The orbit of HD 106906b is highly eccentric, elongated and tilted relative to the plane where the rest of the system's debris disk lies. Something disturbed this planet's orbit significantly. The leading hypothesis involves a close encounter with another star. HD 106906 is a binary system with two Sun-like stars orbiting each other, but there might have been additional stellar companions in the past that since drifted away, gravitationally scattering HD 106906b into its current distant tilted orbit. This planet is important for another reason. It might be an analogue for Planet 9, the hypothetical planet that some astronomers believe exists in the outer reaches of our own solar system. After exploring dozens of bizarre alien worlds, it's worth stepping back and asking, what are we actually learning from all this? Beyond the sheer strangeness and the catalogue of exotic environments, what fundamental insights about planetary science and the universe are emerging from the study of exoplanets? First and foremost, we've learned that planetary systems are far more diverse than we ever imagined. Our solar system, once thought to be the template for how planetary systems work, is actually just one configuration among countless possibilities. The orderly arrangement of rocky planets in the inner system and gas giants farther out, the near-circular orbits, the spacing between planets, none of these features are universal. They're not even particularly common. Hot Jupiters, which don't exist in our solar system, are among the easiest exoplanets to detect and are found around several percent of Sun-like stars. Super-Earths and mini-Neptunes, planets with masses between Earth and Neptune that also don't exist here, appear to be the most common type of planet in the galaxy. Circumbinary planets orbit binary stars in configurations we didn't think were stable. Rogue planets wander through interstellar space by the billions or trillions. The universe is vastly more creative than our theories predicted. Second, we've learned that planetary migration is not just possible but probably common. Planets don't necessarily stay where they form. Gravitational interactions with the protoplanetary disk, with other planets, or with stellar companions can cause planets to move inward or outward over time. Hot Jupiters almost certainly formed much farther from their stars and migrated inward. Some planets might form in the outer system and scatter inward. Others might form closer in and be pushed outward. The final architecture of a planetary system is the result of billions of years of dynamical evolution, not just the initial formation conditions. This has profound implications for habitability. A planet might form outside the habitable zone but migrate into it later. Or it might form in the habitable zone but get ejected or scattered into a hostile orbit. The idea that we can identify habitable planets simply by checking whether they orbit at the right distance from their star is too simplistic. We need to understand the full orbital history and dynamical evolution of the system. Third, we've learned that atmospheres are incredibly important and incredibly complex. The composition, thickness, and dynamics of a planet's atmosphere can completely determine its climate, its temperature, and its potential for habitability. Two planets with identical masses and orbits could have radically different surface conditions, depending on whether they have thick atmospheres that trap heat or thin atmospheres that allow heat to escape. Atmospheric loss processes, driven by stellar radiation and stellar wind, can strip away atmospheres over time, transforming planets from one type to another. A mini-Neptune can become a rocky super-Earth if it loses its hydrogen and helium envelope. A temperate planet can become a frozen wasteland if its atmosphere escapes. Understanding these processes is essential for predicting which planets can maintain habitable conditions over billions of years. Fourth, we've learned that stars are not passive backdrops for planetary systems. They actively affect their planets through radiation, stellar wind, magnetic fields, and flares. Red dwarf stars, the most common type in the galaxy and hosts to many potentially habitable planets, are magnetically active and prone to violent flares that could sterilize planetary surfaces or strip away atmospheres. Understanding stellar activity and its effects on planets is crucial for assessing habitability. Fifth, we've learned that we still have enormous gaps in our understanding. We can't predict with confidence which stars will host planets and which won't. We don't fully understand how super-Earths and mini-Neptunes form, or what determines whether a planet ends up as one type or the other. We don't know how common Earth-like rocky planets in habitable zones actually are, because our detection methods are biased toward finding larger planets in closer orbits. We don't know whether life is common in the galaxy or vanishingly rare. the study of exoplanets has moved from the initial thrill of discovery to the hard work of understanding. Every new planet adds data, but data alone doesn't provide understanding. We need better models, more sophisticated computer simulations, improved instruments, and decades more observations to piece together the full picture of how planetary systems form, evolve, and produce the incredible diversity we're observing. And perhaps most importantly, we've learned humility. The universe is stranger than we thought, and every time we think we understand the rules, we discover an exception. We can't talk about exoplanets without addressing the question that underlies so much of this research. Is there life out there? The discovery of thousands of exoplanets has transformed the search for extraterrestrial life from philosophical speculation to a concrete scientific program with specific targets and measurable goals. We now know that planets are common, that rocky planets exist in the habitable zones of many stars, and that the basic ingredients for life, water, carbon-based molecules, and energy sources are widespread in the galaxy. But knowing that the ingredients exist is very different from proving that life itself exists. The challenge is detection. Life on Earth has dramatically altered our planet's atmosphere. Oxygen, which makes up 21% of Earth's atmosphere, is almost entirely produced by photosynthetic organisms. Without life constantly replenishing it, oxygen would react with other chemicals and disappear from the atmosphere within a few million years. Methane, another component of Earth's atmosphere, is produced largely by biological processes, particularly methanogenic bacteria and organic decay. The combination of oxygen and methane in the same atmosphere is particularly telling, because these two gases react with each other and should not coexist in significant quantities without something constantly producing them. These are biosignatures, signs that life might be present. If we could detect oxygen and methane together in the atmosphere of an exoplanet, particularly a rocky planet in the habitable zone, that would be strong evidence for biological activity. Not proof, because there are non-biological processes that can produce both gases, but strong enough to warrant intense follow-up investigation. The problem is that detecting biosignatures requires incredibly detailed spectroscopy of exoplanet atmospheres. When a planet transits its star, a tiny fraction of the star's light passes through the planet's thin atmospheric shell before reaching us. Molecules in the atmosphere absorb specific wavelengths, leaving imprints in the spectrum. By analysing these absorption features, we can determine what gases are present and in what quantities. The James Webb Space Telescope, launched in late 2021, was specifically designed with the capability to perform this kind of analysis. JWST's infrared instruments can detect molecular signatures that previous telescopes couldn't, including water vapor, carbon dioxide, methane, and potentially even oxygen or ozone. Several rocky exoplanets in habitable zones are already scheduled for detailed atmospheric characterization with JWST. But even with JWST, there are limits. The technique works best for planets orbiting small, cool stars because the ratio of planet to star size is more favorable, making the atmospheric signal stronger. For Earth-sized planets orbiting Sun-like stars, the signal is incredibly weak, requiring hundreds of hours of observation time to achieve sufficient precision. And for planets that don't transit at all, which is the majority, we can't use this technique at all. Beyond biosignatures in atmospheres, some scientists are exploring the idea of detecting technosignatures, evidence of technological civilizations. Radio signals, laser pulses, artificial light on the night side of planets, industrial pollutants in atmospheres, massive structures like Dyson spheres that partially surround stars. All of these could potentially be detected if they exist. The search for extraterrestrial intelligence, SETI, has been scanning the sky for radio signals since the 1960s with no confirmed detections. But the search space is enormous. There are billions of stars to monitor, countless possible frequencies, and no guarantee that any civilization would be transmitting signals we could detect at the exact moment we happen to be listening. A null result doesn't mean there's nothing out there. It just means we haven't found it yet. The discovery of exoplanets has given SETI new focus. Instead of randomly searching the sky, we can target known planets, particularly those in habitable zones. If a civilization exists on one of these worlds and happens to be broadcasting, we now know where to point our telescopes. There's also a more sobering aspect to the search for life. The Fermi paradox asks, if life is common and the galaxy is billions of years old, where is everyone? Why haven't we detected any signs of extraterrestrial civilizations? Why haven't they visited us or left obvious traces of their existence? One possible answer is that life is common, but intelligent technological civilizations are rare. Maybe life gets stuck at the microbial stage on most planets. Maybe the evolution of intelligence requires specific unlikely conditions. Or maybe civilizations tend to destroy themselves shortly after developing technology, through war, environmental collapse, or other catastrophes, leaving only a brief window during which they could be detected. The study of exoplanets has progressed at an astonishing pace over the past 3 decades, from 0 confirmed planets beyond our solar system to more than 6,000. From barely being able to detect giant planets in close orbits to characterizing atmospheres and measuring the densities of rocky worlds. But we're still in the early stages of this field. The next few decades promise discoveries and capabilities that will make our current knowledge seem primitive by comparison. Several next-generation space telescopes are planned or already under construction. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct extensive surveys to find thousands of new exoplanets using gravitational microlensing and direct imaging. It will be particularly sensitive to planets in wide orbits, regions that current transit surveys miss, helping fill in our understanding of planetary system architectures. The European Space Agency's Plato mission, planned for launch in 2026, will focus on finding and characterizing terrestrial planets in the habitable zones of bright nearby stars. Unlike Kepler, which observed a distant patch of sky with faint stars, Plato will target closer, brighter stars where detailed follow-up observations are easier, setting the stage for atmospheric characterization and biosignature searches. Ground-based telescopes are also getting enormous upgrades. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter, making it the largest optical telescope ever built. With adaptive optics to correct for atmospheric distortion, the ELT will be capable of directly imaging exoplanets and taking spectra of their atmospheres, potentially detecting biosignatures in nearby systems. But beyond individual missions, there's a growing recognition that answering the big questions about exoplanets and life will require long-term coordinated efforts involving multiple telescopes, multiple techniques, and decades of sustained observation. One planet with an ambiguous biosignature detection won't settle anything. We'll need to study dozens or hundreds of potentially habitable planets, comparing their atmospheres, looking for patterns, ruling out false positives, building statistical confidence that what we're seeing is real. The technology for doing this exists or is being developed. What's needed is the commitment to build and operate these instruments over the timescales required. That means stable funding, international cooperation, and public support for science that may not produce headline-grabbing discoveries every year, but will gradually assemble a comprehensive picture of planets and life in the galaxy. There's also exciting work happening in laboratory astrophysics. Scientists are recreating the extreme conditions found on exoplanets in laboratory settings, studying how materials behave at temperatures of thousands of degrees and pressures millions of times Earth's atmosphere. This experimental data is essential for interpreting observations. When we detect a spectroscopic signal from an exoplanet atmosphere, we need to know what molecules could produce that signal and under what conditions. Lab experiments provide that crucial information. Computer simulations are becoming increasingly sophisticated. Modern climate models can simulate the atmospheres of exoplanets, predicting temperature distributions, wind patterns, cloud formation, and atmospheric chemistry for different planetary compositions and orbital configurations. These simulations help us understand what we're observing and guide us in deciding which planets are most worth studying in detail. Artificial intelligence and machine learning are also playing growing roles. With thousands of exoplanet candidates and limited telescope time, we need automated systems to prioritize targets, analyze data, and identify unusual signals that merit human attention. Machine learning algorithms are being trained to recognize planetary transits, classify stellar activity, and even predict which stars are most likely to host interesting planetary systems. One of the most exciting prospects involves missions to nearby exoplanets. Not to visit with spacecraft, which remains far beyond our current capabilities, but to study them in unprecedented detail using something called a starshade. A starshade is a large, specially shaped screen that flies in formation with a space telescope, positioned to block light from the star, while allowing light from orbiting planets to pass through. This technique could enable direct imaging and spectroscopy of Earth-sized planets around Sun-like stars, something currently impossible. The concept has been demonstrated at small scales, and NASA has studied several starshade mission concepts. If one of these missions is eventually funded and launched, it could provide the first detailed look at a truly Earth-like planet in another solar system, potentially detecting oceans, continents, weather systems, and if we're extraordinarily lucky, clear evidence of life. We began this journey standing on Earth, looking up at the stars and wondering what other worlds might exist out there. Now, after exploring dozens of alien planets, each one more bizarre than the last, we return to that same perspective, but with profoundly changed understanding. Earth is not typical. It's not the model from which all other planets derive. It's one outcome among countless possibilities, shaped by specific conditions, specific timing, specific accidents of formation and evolution that produced a world where liquid water exists on the surface, where an oxygen-rich atmosphere allows complex life to thrive, where plate tectonics recycles material and regulates climate over geological time, where a large moon stabilizes the axial tilt and creates tides. Change any one of those factors, and you might get something completely different. A world with runaway greenhouse effect like Venus, a frozen desert like Mars, an ocean planet with no land, a scorching lava world, a gas giant with no solid surface at all. Earth's habitability, its capacity to support life as complex and diverse as what we see around us, is the result of an intricate combination of factors that may be uncommon in the galaxy. And yet, with hundreds of billions of planets in the Milky Way alone, even uncommon becomes common at large enough scales. There are probably millions of Earth-like planets out there. Not identical to Earth, each one will have its own unique characteristics, its own history, its own climate and geology, but similar enough that liquid water could exist, that atmospheres could remain stable, that life could potentially emerge and evolve. We don't know yet whether life is common or rare in the universe. We don't know whether intelligence and technological civilizations are inevitable outcomes of evolution, or incredible flukes that happen only once in a billion worlds. We don't know whether we're alone in this galaxy or surrounded by neighbors we simply haven't detected yet. What we do know is that the universe is far stranger, far more diverse, and far more wondrous than we imagined. Iron rains from alien skies. Diamond may form in the mantles of carbon-rich super-Earths. Planets orbit two suns. Worlds wander through empty space with no star to call home. Glass shards blow sideways at supersonic speeds. Dead stars host zombie planets, forged from the ashes of supernova explosions. Every one of these discoveries was made not by traveling to these distant worlds, but by observing them from Earth, by measuring tiny dips in stellar brightness continue, by analyzing the spectrum of light filtered through atmospheres hundreds of light years away, by detecting wobbles in stellar motion so subtle they reveal the gravitational pull of unseen companions. The ingenuity required to detect and characterize these worlds is itself a testament to human curiosity and capability. The exoplanet revolution has given us something precious: perspective. For all of human history, until 30 years ago, Earth was the only known planet capable of supporting life, the only world with oceans and continents and blue skies. It was easy to think of ourselves as central, as special, as the point of the universe. Now we know that planets are everywhere, that worlds beyond counting fill the galaxy, and that our particular combination of conditions, while perhaps uncommon, is certainly not unique. This perspective doesn't diminish Earth's importance. If anything, it enhances it. We live on a world where conditions have remained stable enough for billions of years to allow life to evolve from single cells to the high complexity we see today. That's remarkable. That's worth protecting. The discovery of hellish lava worlds and frozen wastelands and planets being torn apart by tidal forces reminds us just how special it is to have a planet where you can breathe the air, drink the water, and walk on solid ground without being instantly incinerated or frozen or crushed. The search for exoplanets is ultimately a search for context. Context for understanding how planets form and evolve. Context for understanding how common or rare Earth-like conditions might be. Context for understanding whether life is a cosmic accident that happened once or an inevitable outcome that emerges wherever conditions allow. And perhaps someday, context for understanding whether we share this galaxy with other intelligent beings who look up at their own night skies and wonder the same questions we do. We don't have all the answers yet. We probably won't have them in our lifetimes. The universe doesn't reveal its secrets quickly or easily. But with every new planet discovered, with every atmosphere characterized, with every orbital configuration measured, we get a little closer to understanding our place in this vast cosmos. The next time you look up at the night sky, remember that nearly every star you see likely hosts planets. Some of those planets are probably hell worlds, where conditions would destroy any probe we could send. Some are probably frozen and dead, orbiting in the outer darkness, far from their stars. But some, perhaps many, might be worlds with liquid water, stable climates, and conditions where life could exist. We don't know which stars host these potentially habitable worlds, because most of them are too distant and faint for our current technology to detect and characterize. But we will know. In the coming decades, as new telescopes come online and new detection methods are refined, the catalogue of known exoplanets will expand from thousands to tens of thousands, then to hundreds of thousands. We'll map the planet populations around nearby stars with increasing detail. We'll measure the compositions and temperatures of rocky planets in habitable zones. We'll analyze their atmospheres for biosignatures. And with each step, we'll narrow the search for life beyond Earth from a galaxy-wide question to a targeted investigation of specific worlds where the conditions seem right. That's the real promise of exoplanet science. Not just cataloguing strange worlds, though that's fascinating in itself. Not just testing our theories of planet formation, though that advances fundamental physics. The real promise is answering one of humanity's oldest and most profound questions. Are we alone? We don't know the answer yet. But for the first time in human history, we have the tools and the knowledge to actually find out. We know where to look, we know what to look for. We know how to interpret the signals. All that remains is to do the work, build the telescopes, make the observations, analyze the data, and follow the evidence wherever it leads. The universe has already surprised us with the diversity of worlds it has produced. Hot Jupiters that shouldn't exist according to our models, super Earths and mini Neptunes that don't occur in our solar system at all. Circumbinary planets orbiting binary stars, rogue planets wandering between the stars, disintegrating planets leaving comet-like trails of dust. Every one of these discoveries required us to expand our understanding, to revise our theories, to accept that the universe is more creative than our imaginations. What other surprises await us? What new categories of planets will we discover that we haven't even conceived of yet? What bizarre configurations and extreme conditions will challenge our next generation of models and theories? And most importantly, when we finally detect clear evidence of life on another world, what will that discovery mean for humanity? These are not rhetorical questions. They're the active research frontiers of modern astronomy. Scientists are working on them right now, analysing data from current telescopes, planning observations with future instruments, developing new techniques for extracting information from faint signals, refining models to predict what we should see under different scenarios. The story of exoplanet discovery is still being written. Every month brings new announcements, new detections, new characterizations. The field moves so quickly that any attempt to provide a comprehensive overview is outdated almost as soon as it's completed. By the time you're watching this video, there are probably several more planets confirmed than when the script was written. That's the nature of a scientific revolution in progress. But the core message remains constant. The universe is full of worlds, each one unique, each one shaped by the interplay of physics, chemistry, and chance. Some are familiar echoes of planets in our own solar system. Others are so alien that we struggle to find words to describe them adequately. Together, they paint a picture of a cosmos where planet formation is a natural, inevitable process, where the raw materials and physical conditions exist in abundance to create worlds wherever we look. Earth is one planet among billions in this galaxy alone. We're not central. We're not unique in our existence as a world. But we might be unique, or at least very rare, in hosting a biosphere as rich and complex as ours, and in producing a species capable of asking questions about the wider universe and developing the technology to find answers. That capability, that curiosity, that drive to explore and understand is perhaps the most remarkable thing about humanity. We can't travel to these distant worlds, not yet, perhaps not ever if the distances prove too vast and the timescales too long. But we can reach out with light, with mathematics, with instruments that extend our senses across cosmic distances and touch these alien places with our minds, if not our hands. The exoplanets we've explored in this journey are real. They orbit real stars, they experience real physics. And somewhere out there, perhaps on one of the Earth-like worlds we haven't discovered yet, perhaps on a type of planet we haven't even imagined, there might be someone else looking up at their sky, seeing our sun as just another faint star among thousands, and wondering the same questions we wonder. Are we alone? What other worlds exist out there? Is life common or rare? Does intelligence emerge inevitably, or only under special circumstances? We don't know yet, but we're looking, and that perhaps is answer enough for now.